Okay, let's start with the last topic, error correction. It is relevant, I think, because after you have learned all the hardware for the qubits, you realize that it can have a lot of error, right? Because it's just an analog circuit. Although some people would like to say that this gate-based model is digital quantum computing and optimization model, right? You use it to do optimization, like the D-wave is analog computing. But I don't really agree with that classification. This is just an analog for all of them because we rotate the qubit by the angle, right? It doesn't have the regenerative feature that we have in the CMOS. So error correction is very important. So let's first have a overview why there is a problem, right? So in classical error correction, we use the easiest one, right? Simplest one might not be the most effective one is repetition code, right? If I have 0, then I encode it with 3 bits. I have 1, encode it with 3 bits. And then if any of them got flipped, then I use so-called majority vote, right? This is very easy to understand. Like I call you on the phone, tell you the number. If it's noisy, I just keep repeating, right? I say, okay, today I got 100% in my exam, right? You say what, 100 or 90, right? I keep repeating. Eventually, you trust that you actually hear 100 because most of the time you hear 100, right? But can we do this in quantum computing? We cannot do that because when we do this repetition, it means you need to copy. We can copy the basis state. There is no problem because we can measure and copy. But for a general wave function, psi equals to alpha 0 plus beta 1, you can never copy. There's no way to copy it, right? You can prove it, right? Met a lot of places to see how it proves. Of course, I mentioned in my book also. You try to prove it, you find that it's contradictory. You can never copy an arbitrary state. So this is the so-called no cloning theorem, right? If you're interested, you can look at the old video in another class, E225. Then what can we do? We actually came up with something similar to repetition code. And another thing is that we use so-called syndrome measurement. So what I see, just like the doctor, right? This might not be a very appropriate analogy, exact analogy, but just think about if I feel that I don't feel well, I go to the doctor, I say, I don't know if I have flu, regular flu or COVID, right? If the doctor is super experienced, like machine learning, then he will just look at my syndrome, right? How often do I cough? What's the fever? How does the fever fluctuate? Then maybe without really testing my blood, the virus, let's assume there's something called collapse virus. Once you test it, it will just explode and then infect everywhere in the world. So you cannot measure the virus. You cannot test it, right? You just look at the syndrome. Then maybe you know that whether I have a regular flu or COVID, right? And then you apply the correct medicine to fix it. That is something like this. So in order to do this error correction, we do need to go through some entanglement. Okay, so that is syndrome measurement. So this is an overview. Let's look at one particular case. This is the so-called bit flip code. In this bit flip code, what our goal is to transmit this alpha 0 plus beta 1. Now, we decided to entangle it with 2 auxiliary bits or ancillary bits. Okay, these 2 are useless. It's not the information we want, but they are very important because they can help us to recover the information. So what we do is to do a NOT gate, control NOT gate. Now you see control NOT gate, you know it is related to entanglement, right? So what do we do? So when we start with alpha 0 plus beta, alpha 0 plus beta 1, now I have 3 qubits. So the state is 0, 0, 1, 0, 0. Is this okay? Everyone okay with this tensor product, right? This is very important, fundamental, cannot mess up, right? And then we apply control NOT gates. What does control NOT gate do? Very good. Flip the target qubit from 0 to 1 or 1 to 0 if the control qubit is 1. Otherwise, do nothing. Okay, so again, in my hints, I told you that you need to know the matrix multiplication. You need to do that well. So practice. I had something similar in the midterm, and then we have some circuits, right? Earlier in the semester, we do this matrix multiplication. So this is a big hint. You need to be able to understand the circuit and how the matrix and vector evolve. Okay, yeah.
For the matrix multiplication, would you use states that have 3 qubits like that?
I won't tell you now. Okay, but I already say matrix multiplication. Okay, so you need to have that skill, practice the skill. Okay, make sure that you know where does the vector evolve from left to right or right to left. I don't want you to make this mistake, right? Vector in the circuit go from left to right, but in matrix multiplication, you go from right to left, right? Don't make this mistake. I cannot help you if you make this mistake. Okay? But here we're just using the bracket notation. We are not using the matrix multiplication. I hope that you are able to do matrix multiplication. Okay, so based on this, what will happen? Let's say after this entanglement, what will happen? Because the control bit, right? This is the control. Right, this is the control bit, and this is the target. Both of them are the target qubit. What happened to this? Because it is a linear superposition, the control bit is 0, then do nothing, because this is control not. So that's why 0, 0, 0 is still 0, 0, 0, right? But 1, 0, 0 become 1, 1, 1. And that's why this is an entanglement, right? This is a perfect entanglement. Okay, let's say we go through a big gate, but this is can be just the noise. It can apply to any of these qubits. Now that is something you need to be aware of. We did not go into detail. You add more qubit to do error correction, you will bring in more error because these qubits are not going to be perfect. So you need to have a small enough error rate or high enough fidelity for your physical qubit in order to add more qubits, right? So that is the challenge that you need to keep the balance, okay? So let's go back to here. Let's say, very unluckily, we flip the first qubit. That's why this is a bit flip code, right? We only deal with the flipping of the qubit. Then the first qubit, when you say you flip a qubit, basically you say you apply a NOT gate to it, right? For example, this is like what? If this is the MSB, right? LSB. You understand what's MSB and LSB well, right? Then this operation is just what? C is what? Can you tell me? What will be the operation for changing from here to here? NOT gate for NSB. And then how will you write it? I want to apply to 3 qubit.
Yeah, so then the tensor with I.
Tensor with I. Yeah. Right? This is a basic thing, right? If you cannot do this basic thing, you cannot do the exam. Okay? If you don't understand, practice. Okay? So I flip this one, right? So in principle, I can write this in vector form. I write the matrix, I will get this also. Okay? Okay, that's okay. Now, got flipped. We cannot measure it because it's quantum state. So what do? We entangle this one more time. What will happen when we entangle it? When this is 1, then I'm going to flip the second bit, and then next time flip the third bit. So I get 1, 1, 1. Correct? Because the first time I get 1, 1, 0. The second time I get 1, 1, 1. The first one is 0, I do nothing. Okay? And then I have this automatic correction at the end, which is reverse. This is what type of gate? Do you know? Did I mention this? Portfolio gate. Control not. Maybe I did not mention at the beginning, but this is control not. Which means if both of them are 1, I'm going to flip it, right? So look at this. The last 2 bits, right, is 1, 1, right? Because they are LSB. Then I'm going to flip this to 0, 1, 1. These two are 1, 1, right? Then I'm going to flip it, become 1, 1, 1. Okay, so in this whole process, again, these two are not entangled now. I can take these two out. This got corrupted, but I still get alpha 0 plus beta 1. Okay, yeah.
Would this work if there were flip sides? So
No, it only work for one flip. Yeah, that's the
also
problem.
it's-
No, if ancilla flip, there's no problem. You just go through this. I have this here, go back to practice. But only one qubit. If you have two qubit flip at the same time, then this doesn't work. Okay, but of course then we will start saying, let me erase this so that you know what I mean, right? This not. The probability of getting one qubit flip may be p, another qubit may be p squared. So this can be pretty low, right? So you need to improve the technology until the p square is low enough if you want just want to use this. Okay, good. So any questions? Yeah.
So I guess to build layer correction, you need multi-bit entanglement, isn't it? You need to, so let's say
Yeah.
if I
Here you have 3 qubit entanglement.
So let's say for 5, I need to multiply.
Yeah, this is just a simple example. Yes, you need to entangle all of them, but this is just simple example. You use 3 qubit, right? Let's look at another example. You may say, how about you have a phase flip? Phase flip, basically, here I use not tensor product I, tensor product I, right? What if I have something called Z, tensor product I, tensor product I? Okay, this is related to maybe T2, right? So what do we do? Now, it turned out that this is also easy. What we are going to do is treat it as a bit flip, okay? But then if we add the Hadamard gate to it, it's equivalent to the phase flip, okay? Because H equal to Z. Am I right in this one? I think so, right? So the phase flip is just the bit flip. So what we're really doing here is this. I first entangle here. Let me see if I have anything. Yeah, I start with this one. This is the information I want. Again, I do entanglement, so I have 0, 0, 0, 1, 1, 1. Now, I can analyze the phase flip by assuming the whole thing is just a NOT gate and then with the Hadamard gate. That this whole thing, right? If I put this as NOT, this is just a modeling of the error. Then this whole thing is just equal to this one. Okay? Why is that? Because the Hadamard gate is going to change my 0 to plus. Remember this? Hadamard gate applied to 0, it will be superposition, right? Which is plus. And then this is minus. Okay? Yeah.
Should include both Hadamard, right?
What do you mean by both
Right now,
Hadamard?
you're blindly close the first Hadamard phase, but not the second Hadamard after the phase.
What my line? This is H and then X and then H.
Okay, so that should be equivalent to.
That equivalent to Z. Yeah. Okay, so I here just go through the math, right? And then you have a bit flip, right? Because after here, bit flip means what? Means from plus becomes negative, and then negative becomes plus, right? It's a bit flip in this space. Okay? And then with this, then you go to here. It is just equivalent to have the bit flip, right? So then we just do the correction. Again, I forgot I have all these things, right? You will get back the same result that like what you did before. So you do need another circuit to handle the phase flip. Actually, sorry, actually, I'm wrong here, actually. I'm wrong, I'm sorry. What I'm saying is this. This one is the phase flip. This is the phase flip. Okay? And the circuit is that we have this Hadamard gate here is equivalent to, it help us to correct this phase flip. Because this is, if you apply this to here, it becomes just a bit flip circuit. So you have an error that is phase flip. You apply Hadamard gate in front of behind it, is equivalent to bit flip. So that's why I can apply exactly the same bit flip correction circuit to fix it. Yeah.
So when you put HX, H, that would be just for the first qubit up there?
Yeah.
Right. So if you were just to replace that block, you could replace that with HX, H within that block, just for the first.
Indeed, yes. In this particular case, right, because I only flip here, right? So this is equivalent to this. H, X, H, H, I, pressure, and then H, I, H.
Those are extra H's though?
Where extra H? This is H, and then X, and then H. This is H.
Well, I was.
Huh?
Z, right?
Z, sorry.
Yes, my question is replace that Z with additional H gates, and within those H gates it's X.
No, the point is,
That's what I'm-
this Z is given by the noise. You cannot control it.
Right.
Yeah, so this is just Z.
Well, yeah, because I was just asking because you put it equal to Z. So I was saying. since they're
Equal to Z.
You should be able to replace Z with HX. Since remember.
You mean this one replaced by HZ?
That's Z.
Yeah, you can do that, yeah, for your analysis. But the noise actually come from as Z, right? Because that is the environment noise that did the phase flip for you. So it is Z. Yeah, you can put H, then become X, right? That is why the rest I can treat it as a bit flip. Yeah.
Do we often see like full bit flips in quantum computers? It seems like most of the way we implement our gates is by like doing a timed pulse. So I would imagine like what's more likely is that it's just like slightly off rather than a full flip than we expect it to be.
Yeah, I don't know this well, but the point is that I'm going to talk about this. In general, if you have this bit flip gate and the phase flip gate, you can do the correction of anything. Yeah, it just mathematically they show that. Yeah, I did not go into the detail. So yeah, that is something, you have a great question and I was not able to really answer you. But just this tool will be enough to make the correction. So then, how do we correct both the phase flip and the bit flip? You have the so-called Shor 9-qubit code. So you encode with 9 qubit gates for 1 qubit to do this correction. But then people have been improving. The smallest one is 5 qubit. They are able to do 5 qubit encoding, and then they can flip both the phase and also the bit flip. Okay, just for you to know, right? There's something I encourage you to study later is the so-called stabilizer. This concept is very useful. Based on this, you will be able to discover new code, right? Because when Shor invented this just because he's smart and come up with this algorithm. But if you want to continue to derive something not that intuitive, then you need to understand the concept of stabilizer, right? So you can think about that. So the last topic I want to talk about is the Shor's 9-qubit code. Okay, it has quite some math, but it helps us to understand the things deeper. So what is that? So the goal is this. I have the 0 state. I'm going to encode. This is encoding with 9 qubit gates in this way. 1 over square root 2, 0, 0, 0, plus 1, 1, 1. And then I'm going to do it 3 times. Yeah, this is, I hope that you understand what I'm talking about. How many qubits do we have here, based on what I'm writing?
9.
9 qubit. Do you agree? Here to here is a tensor product, right? Here to here is another tensor product. So I have 9 qubit, and here I have how many qubits? 3 qubits, and they're in a superposition of two basis states, 0, 0, 0, and 1, 1, 1. Okay? So this one I definitely can write it as 1 over 2 square root 2, 0, 0, 0, plus 1, 1, 1, and then 3 of them, right? Tensor product. So if I have a 0, I will encode it by 9 qubit in this way. Okay? And then if I have 1, then how do I encode it? I'm going to encode it in this way. 0, 0, 0, minus 1, 1, 1. And then again, I repeat it for 3 of them. Maybe to save the space, I just write this. I hope that you understand what I mean now, right? 9 qubits. 3 groups, 3 tensor products of the tensor product of 3 subspace. Each subspace has 3 qubits, right? And the code is 0, 0, 0, minus 1, 1, 1. Again, linear superposition of 2 basis states, right? So then what does it mean? Then it means we will transform this to this, right? And maybe I should make it clear. Then we call this one 0. Let me call it 0s, right? The encoding one, 1s, right? When I say 1, it's no longer 1 qubit, just a notation. Okay, it means 9 qubit. This is the encoded 1 and encoded 0, right? So basically, we are saying that if I have alpha, or the psi, I'm showing in this figure, psi equals to alpha 0 plus beta 1. I encode it as alpha 0s plus beta 1s. Is that okay? Okay, let's say, unfortunately, I have some error. So what is the meaning of error? Any quantum state, it should not lose its information because everything is quantum. The reason that it loses information because it leads the information to the environment. It entangles with the environment, right? So we might have an environment state originally, right? Maybe I say with the environment, I call it E0, right? So the original state is what? E0 psi. Are you okay with what I'm writing? I include the environment state and combine it with the qubit state I'm interested in. Again, the tensor product, right? You can even think, oh, maybe this is another qubit and you don't want it, it's just an environment, whatever, right? Then what happened? It transformed to what? This is equal to alpha E0, 0 plus beta E0, 1. However, I encoded it already. I assume I already encoded it. Right? Then that means it has 9 qubits. Okay? It becomes this. Okay? So I assume that due to error, and this error comes from the environment because it entangled with the environment. Right? If the environment has no effect on the qubit, if the environment has no effect on the qubit, then it will just keep as this, right? And I discard the environment, I get back my psi because they are not entangled. But now, let's say somehow they got entangled, then I will do it one by one. E0, the E0 state with 0s, maybe becomes A0 0 plus A1 1. This is very general. That will answer your question, right? The rotation is not bit flip or phase flip, right? It's just any possibility because I can have any combination with A0. A0 and A1 can be anything. That it means and then if you look at your qubit, right, it becomes a very general possible state. Yeah.
At what point on the circuit is this red state? Because it's initialized to all the other.
The red state here is here. I think it is here. I think so. Yeah, I did not check, but I think so. Okay, maybe you can try to check. It's here. Yeah. Now, then I also assume E0 of this guy becomes A2 0 plus A3 1. Okay, just that I have this just have this error entanglement, right? So this is just an entanglement. Entanglement with the environment. Okay, and I'm going to consider them separately because it is linear. Okay, so let's look at this. What I'm trying to do is just rewrite what I had, right? So now I just rewrite the whole thing. We have E0. Originally, it is alpha 0s, 9 qubits, 1s, right? This is before the error. This one, right? I'm trying to write it again. And now I will spell it out. This one equal to what? Equals to E0, 2 square root 2. Maybe for your study, let me call this equation 1, right? So actually, I'm just repeating equation 1, okay? So what is this alpha 0? It is alpha. Do you remember how we encode 0? Thank you. 0, 0 plus 1, 1, 1. But you have 3 qubit. Yeah? You have 9 qubit. And then plus beta 0, 0, 0 minus 1, 1, 1, which is the encoding for 1, right? And again, do this, right? Now, to simplify, right? Since the last 6 qubits are not entangled, right? Because we assume, here I only give you one of the possibility that because we assume the first qubit has error, right? We keep only assuming only one qubit. We have 9 qubit. We assume the first qubit has error, like what we're showing here. Only the first qubit has error. Then I will just ignore the last 3, the last 6, just to ignore them in my derivation, right? So ignore last 6 for simplicity. Okay. So with how many pages? So with this, then I have this. The first one is again E0 divided by square root 2 and then times alpha 0, 0, 0 plus 1, 1, 1 and then this is for this one. Okay, that's the first term, right? And then, of course, the whole thing is going to be plus E0 divided by square root 2 beta 0, 0, 0 minus 1, 1, 1. So I did not do anything new, right? What I'm doing is just ignore the last few qubits and then rewrite this equation before having error. That is how you entangle with when I combine the environment and this one, right? Now, and then when there is an error on the first bit, when there's an error on the first qubit, Then I'll just repeat what I say here. This E0 applied to 1 is going to give me this. Actually, I need to do it one by one. Right? I will go this one first. Okay, when E0 applied to alpha, what do we get? I take this out, alpha divided by square root 2. This is alpha divided by square root 2. And then E0 applied to 0, right? E0 applied to 0 becomes A0, 0, A1, 1. Actually, now I realize I should not put this S because I only want to talk about 1 bit. The error come to 1 bit, right? So it becomes, when this is 0, I have A0, 0, 0, 0, right? Plus, maybe I factorize it, then it will be better. Plus A1, 1. The whole thing, right? Why I have this? Because this E0, 0 become A0, 0 and A1, 1. So this is E0, 0 become A0, 0 and A1, 1, right? This whole thing, tensor product with 0, 0, plus A2, 0, plus A3, 1, tensor product of 1, 1. Do you see that? Because this only applies to the first qubit, to the last 2 qubits, I keep it as it is. 0, 0 is still 0, 0. 1, 1 is still 1, 1. But I then have E0 to 0, right? E0 to 0, as I show you, becomes A0, 0, A1, 1. It's just that a general state. And E0, 1 becomes A2, 0, and A3, 1. That's what we have here. Okay, so this is the state that we have. Okay. How about for this one? We have similar thing. We have beta divided by square root 2. Let me test if you all understand. What will be the first item? When I apply beta, when I have error, E0, 0 becomes what? Right? This E0, 0 together. When I have error, flip the first bit, it becomes what? It becomes A0, 0 plus A1, 1, right? So it is the same. It becomes A0, 0 plus A1, 1. The whole thing tensor product 0, 0. Minus, what is the second one? A2, 0 plus A3, 1. Very good. This is the first qubit. Tensor product of 1, 1. Everyone can follow? Any question? Just ask, right? Up to now, you see this is pretty nice. Actually, the 0 and 1, they're repeating each other. That means later you can factorize them. Why is that? Now, I will continue to do this. But if I do this, I think it will be difficult for you to see. But I will still do it. What I'm going to do now is multiply A0. This is 0, 0, 0. This is 1, 1, 1. Right? So I have A0 times 0, 0, 0. And then what I'm going to do is to split it so that I have this. I know it is from the last page, right? From the last page. Let me write it down first. I can change what I had from the last slide to be this. A0 plus A3, right, times 0, 0, 0 plus 1, 1, 1. And then the whole thing plus A0 minus A3 times 0, 0, 0 minus 1, 1, 1. Right? I don't think you need to be able to follow now. I will just show you what happened. And this is just math. You can do it easily to show that this is correct. Now, let me finish writing. Sorry for that. Very long, right? I know it is very long, but you need to see it at least one time in your life. 1, 0, 0. And you need to understand why they were able to come up with this, right? I claim that this whole term equals to this one. Okay, let's see if that is the case. For example, how many 0, 0 do I have? I only have A0, 0, 0, 0, right? But here, how many 0, 0 do I have? I have A0 plus A3, 0, 0, 0, A0 minus A3, 0, 0, 0, right? But this is negative, this is positive, right? So they are going to get cancelled, so I have 2A0, 0, 0, 0. But I divide it by 2. So if you expand it, you only get 1, 0, 0, 0. That is what we have here, 1, 0, 0, 0. How many 1, 0, 0 we have? We only have one, A1, 0, 1, 0, 0, right? If you look at this, how many 1, 0, 0 we have? I have 2. But then I have A1 plus A2, A1 minus A2. So when you add them together, I only have 2A1, 1, 0, 0. Divided by 2, again, it is correct. Yeah.
We understand
Yeah.
MSB is.
No, error is on the MSB. Yeah. MSB is, error is the MSB. Right? So these are the error, right? Uh-huh. Say again? Huh. Let's don't call it error. Let's call it the environment state. Okay? And yes, but when you entangle with your qubit, it becomes an error of your qubit. Yeah. So originally I have very pure 0. Now it becomes something 0 plus something 1, right? I don't know whether it's 0 or 1. But the point is that now by using this 9-qubit code, I come up with these 3 states. But what is the correct state? The correct one is what? This is the qubit, right? That we want, right? The 3 qubit. The correct one supposed to be what? For alpha. What is the correct one supposed to be? Let's look at, before we apply the error, what is the correct one? 0, 0, 0 plus 1, 1, 1. 0, 0, 0 plus 1, 1, 1. Okay? And of course, the last 9 qubits are the same. We do not talk about it. Now, let's take a look on the beta part, on the one part, the beta part, which was the original one of this qubit. What is that? Let me also copy it. Beta over 2 square root 2. Again, you don't need to copy because next page I have the whole equation, right? But I want you to appreciate what is so good now, because now you have try to see what are the commons between the 1 and 0, or the beta and alpha. And do something.
So one of the terms for these when the beta survives, beta 111, is that what you're getting at?
What you get is, do you see that they have the same environment in front of them? Well, but these are not the same. however, um, yeah, but they have the same environment. Now, so then that is how you do the correction, right? So here I show you the final results again. That's why you don't need to correct. Here we don't have the last 6 qubit, but the last 6 qubit are the same for all of them. Okay? So that is what we do. So we will measure, we did not show here, right? Did not show. Yes, this is only the first 3 because we only have 3 qubit here, right? And then, but the last qubit is just 0, 0, 0 plus 1, 1, 1. The last 6 one, 2 of them. Yeah. So you are going to have 0, 0, 0 plus 1, 1, 1, 0, 0 plus 1, 1, 1 for each of these superposition, right? So what we will do is to do an entanglement. With the auxiliary bit. Or ancillary bit, maybe let's call it ancillary bit. Right, not shown. And then we will measure the ancillary bit. And you will find that when you measure them, they actually have the same syndrome. For example, like if there's no flipping, what should I expect? If no flipping, right, or no error. If there's no error, we expect the output to be what? We expect it to be 0, 0, 0 plus 1, 1, 1 alpha plus beta 0, 0, 0 minus 1, 1, 1. Correct? Because this one is the encoding for 0. This is the encoding for 1. I did not show the other 6 qubit. Correct? If there's no error. So if we do the correct encoding of this, we do an entanglement of this qubit with an auxiliary bit. We measure the auxiliary bit. We find that, oh, that is correspond to this. Then you do nothing. You just apply an identity gate, right? Now, if, for example, you got, let's say the second row with second row, I mean, what I mean is if the auxiliary bits the auxiliary bit is not shown in this circuit, but we will do some entanglement with this. We can always entangle the state with the auxiliary bit, okay? And then we measure the auxiliary bits. Based on the value of the auxiliary bit, I will know that whether it is this state or this state. Yeah.
So your, I guess, calling it ancillary bit is what's got the
Ancillary, sorry, not auxiliary.
So that's the error syndrome, right?
Yeah, there is a syndrome.
But can you maybe point where are you in the circuit? When you
Not in this circuit. We
The
did not show
circuit
that.
on the-
No, this one doesn't have the ancillary bit.
Yeah.
So because this one come up with some auto correction. So in a real case, you actually need to go to the ancillary bit, you do measurement, and then you apply. Okay? Here is no ancillary bit. Ancillary bit.
So what is
This one is just based on the result, it automatically correct. Okay, this is not the original Shor's circuit. Okay, just that it is not shown here. Okay, Yeah.
Shores, you have to do some combination, classical.
you need to do the measurement.
Yeah, and then your gate post that change depending your result.
Your measurement will indicate whether you are in which state you are in here, what type of flipping you have. So you can see that from this whole exercise, it gives you a general error. But this general error eventually decomposes to these 4 types of possible output. These are the Bell states. Okay, and then because if you entangle these Bell states with ancillary bits, by measuring the ancillary bit, you know that which state it becomes. And then you apply the appropriate correction. So if the ancillary bit tells you that it is, for example, there is a wrong side, for example, the second row, right? Then you know that, okay, actually what I have is this second row. So what should I apply in order to get back what I want? So this, I am supposed to get this and this, right? But now you can see that this is a what? Sine flip, this is a phase shift, right? So I will apply Z gate, right? You apply a Z gate, then you can bring it back to the correct answer. Okay, so I only show you how it works. I don't have insights for you how they came up with this, but the most important thing is you see that it was done such a way that the 0 and 1 encoder 0 and 1 have shared the same environment value. That's why you can factorize it out. If they don't share the same value, you cannot factorize it out, right?
So let's say if the environment for the MSB is different from the LSB, then this regime doesn't work.
You cannot, because I already proved a general case. These are the only 4 possible values. Yeah. This A0 minus A3, A0 minus A3, this is the environment qubit state, right? It's a superposition of 2 states of the environment that they have the same, right? So when I add them together, I can factorize it, and then my qubit still in this state, right? Yeah.
But don't you think this is a big limitation of this algorithm? Because assuming that the environment of all the qubits is the same, is that a safe assumption?
No. We did not do any assumption again, right? I just assumed that it will go into this combination. There's no assumption at all. This is very general. And then when you derive full, you get this. And that's the great thing about this algorithm. No matter what error you have, you come up with the same environment in front of the flip content. Yeah?
Okay. It seems like you the ancillary bits.
Yeah.
And you never have to measure the data qubit.
You should not measure because it will collapse. You never should measure. Yeah. To the data qubit. Yeah. Based on what you measure in ancillary. Okay? Okay, so I will just stop here for this. And thanks for going through. And the good news is that, what's the good news? The good news is I'm not going to test this.